No, we're not doing that.
Wait,
Okay.
do we have to do we have to add it in like base 2 and base 3?
Yeah, let's do it here.
We
All
can't
right.
we can't convert it and then add it.
It's actually easy. Look, I'll show you how to do it easy. Hang on. Hang on. All right, so let's start. Okay, we're starting a new section, so let's make a new worksheet. Did anyone make a new worksheet? Yes? No? Okay, here it is. New worksheet. All right, name it. What is it? 5.3. What it is, right? What are we talking about? Bin, OCT, hex. By the way, we haven't. I don't know if we said this, but why is it called hexadecimal? Huh? We're done with 5.2. I don't want to do that problem. We're in 5.3. We're on page 81. Well, actually, why don't we just go straight to the exercises? 85, is it? Go straight to page 85. We're ready. We're ready, baby. Are you ready? All right, we're going to focus on binary, octal, and hexadecimal today. Hexadecimal means what? Base 16. Why? Because hex is Greek for 6. And decimal is Greek for 10. So 6 and 10 is 16. Octal is base 8. Binary is base 2. All right, your name.
16 or 6?
Hexadecimal. 6 and 10. 16.
Oh,
All right. And today's date, what is it? The 2013.01. What the heck is today? 2/4? Is that 24th yet? All right, let's go straight to question number 1 on page 85. Right? What is the largest integer that has 7 binary digits? No, binary. 1, 1, 1, 1, 1, 1, 1. Right, there you go. Amazing. Can you convert that to decimal? They want to know how big that is. How do you convert? Isn't that the int command? How does the int command work? If you put in any old int in here, it'll convert it to base 10. But if I don't say what base it is, it stays the same base. It is base 10. But if I want to convert to base 2, I do that. What'd I do? Trace back. Yeah. What happened here? Base 2. Oh, I'm sorry, I said it wrong. If it is a base 2 number, it'll convert it to base 10. Like this. Right, okay. But we want what? 7 sevens? 7 ones? Boom. 127. Now look at this pattern. The 1 in the what? Place. 1's place. 2's. 4's. 8's. 16's. 32's. 64's. What would be the next one? What's 128 minus 1? That always works out. If you have 7 bits, the largest number you can represent in 7 bits is 2 to the 8th minus 1. 2 to the 0, 1, 2, 3, 4, 5, 6, 2 to the 7th minus 1. Isn't 2 to the 7th 128? 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 32 times 2 is 64 times 2 is 128. All right, so if you want to know what the largest 7-bit number is, you do 2 to the 7th minus 1. So why is this 63? Because it's 2 to the 6th, which is 64 minus 1, right? Okay, so anyway, they wanted that, so I'll leave it like that. Okay, what else did they want? How about 15 digits? All right, 1A and number 1B. All right, 15 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. In base 10, 2. This is 5-3. 5-3. I skipped question 10 and question, I forget, 6. I don't want to get into that. Question 10 was about, was it Roman squares or magic squares? I don't want to get into that. And question 6 was about Sudoku. All right, look, this is the topic. Binary, binary, octal, and hexadecimal. What? Well, the first one is 7, and this one's 15. All right, so let's go straight to asking Sage. Int of that in quotes. Just copy it. Comma 2 is there. Okay. 2 to the 15th minus 1. So what is 2 to the 15th then? 32,768. Perfect. Very nice. All righty. Now, number 2. Was that terrible? All right, so we have functions that convert to base 10. We have functions like bin, oct, hex that converts to bin from base 10. But how do you do number 2, converting from base 16 to base 2? We know how to convert to base 10 or from base 10. Some Sage commands can do it, some we had to do by hand, right? But we know how to convert to base 10 multiplied by the power, by the places, right? We know how to convert from base 10, divide by the base you're going into. We know how to do it. But how do you convert from base 16 to base 2? That's what they want. That's different. Oh. All right, let's see. This is what they want. They want you to convert 90 AB from base 16 to something in base 2. You okay? You need a napkin? Yeah. That'll be 5 cents? Okay. So how do you do that? Actually, it's very easy. What is the biggest hex digit?
What is hex 7?
Hex is base 16. Hexadecimal. Hexadecimal. 6 and 10. Base 16.
15.
15, right? Okay. That's the letter. Isn't there a digit for that? What was the biggest digit in hex? The letter. F, right? All right. Now, isn't 15 one of these kinds of numbers? Right? Isn't 15, let's do this one. Isn't it just 4 of these? Because 2 to the 4th is 16 minus 1 is 15, right? So look at this. The largest 4-bit number you can write, it's the largest hex digit there is. What am I getting at? Every 4 bits can be converted to 1 hex digit. Right? Because if you count from 0, 0, 0, 0 in binary to 1, 1, 1, 1, 1, you get from 0 to 15. And those are the digits in hex, aren't they? Oh, okay. Let's leave this the way it was. Right? Okay, so let's see. This would have to be, I could do this as a comment. Okay, ready? I'm going to make this a comment. Okay. Or you could use the word processor if you want. How do you write 9 in 4 bits? I need 1, 2, 3, 4 places, okay? Now, the 1's place, the 2's place, the 4's place, the 8's place. Do you need an 8? Yeah. Okay, do you need a 4? No, because 8 div 9 goes once, remainder 1, right? So do you need a 4? No. Do you need a 2? No. Do you need a 1? That was the remainder. That's the 9. All right, I'm going to separate this out. I'm going to do the 9, I'm going to do the 0, I'm going to do the A, I'm going to do the B, separate. All right, let me line it up. How do you write 0 in 4 bits?
0.
Just 0?
Yeah.
No, 4 bits.
4 zeros.
4 zeros. Okay. What does A represent? It's right after 9, so 10. All right, let's go. All right, so what is, remember I'm doing 4 places, right? What is, 1, 2, what is 8 into 10? What's 8 div 10? How many times does 8 go into 10 at most? 1. So I need an 8. What's the remainder? 2. That's the mod, right? So do you need a 4? No. Do you need a 2? Yeah. Do you need a 1? No. Perfect. Okay. What does B mean? 11. All right. So what's 11 div 8? 1. What's 11 mod 8?
1.
No.
0.
3. What am I saying? Mod is remainder. 11 div 8 means how many times does 8 go into 11 at most? That's once. 11 mod 8 is, what's the remainder? 3. Okay, so do you need a 4? No. Do you need a 2?
Yes.
Yeah, because 3 div 2 is 1, remainder 1. That's it. Is that terrible? There's a 1-to-1 correspondence with each single digit in hex and every single 4-bit number you could write. How's that? Is that easy? It's very easy to convert from base 16 to base 2 and vice versa. All right. That's what we did. What? A means 10.
A means 10.
Right, because it counts 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C. A is after 9. And they need him now? No, 12:05. Okay. Mario, you've got mail. Remember AOL? Anyone use AOL anymore? You say, you've got mail. Didn't it talk to you? Yeah, 1205. They need you. 1205. It's not complicated. Okay. All right, that's number 2. All right, let's go backwards. Number 3 says convert binary to hex. Oh, okay. Can you just do the same thing backwards? All right, let's write down the problem. It's 0101, 0101, 1101, 1101, 011. Is that it? Am I missing anything? 0101, 1101, 011. Yeah, that's it, right? All right. So what I want to do is convert that binary number into hex. We used to say base 2 and base 16, same thing. All right, now wait, how are you going to group it? You got to group this. Shall we group it from the right? Because notice, it's not a multiple of 4, the number of digits, is it? If you want, you could put a 0 in front. You want to do that? Right, you have to have this in bunches of 4, because I know how to convert 1 hex digit to 4 bits, or vice versa, 4 bits to 1 hex digit. I have to do this in groups of 4. So this would be the lowest. This would be the ones place in hex. This will be the 16's place in hex. This will be the 256 place in hex. Notice you could throw a 0 in there if you want, right? So let's break this up a little bit. Boom, boom. All right, let's start. Well, let's start right there. What does this mean? Just these 3 bits. A 2. So how do you write 2 in hex? Is there a digit for 2 in hex? And what is it? It's 2. This is not tough. Okay. What do these 4 bits represent?
1, 2, 3, 4, 7, 9.
9? What? 14. A 1 in the 2's place, a 1 in the 4's place, and 1 in the 8's place. 8 and 4 is 12, and 1 is... 8 and 4 is 12, and 2 is 14. All right, so how do you write 14 in hex? What digit is it? No. What did? There's a digit. Yeah. Okay. Victoria, you've got mail. All kinds of mail today. Wait, now you were saying what? What digit represents 14? E. If F is 15, E is 14. Okay, E. E is 14. Z would then be what? 13, right, okay. Well, so what is this guy? How much is this? Is 1, a 2, and an 8? 11, right? How do you write 11? B. A is 10, remember. There you go, done.
Wait, A is 10 and B is
A is 10, so B is 11. That's 11, isn't it? A 1 and a 2 is a 3, and an 8 is an 11. Right? Okay. All right, is this terrible? Converting from base 2 to base 16 and back is easy. Right? Not very terrible. All right, how about this? Number 4 is different. Any questions up to 3? We okay up to 3? All right, number 4 says convert from hex to octal. Wait, that's different. All right, here's our hex. F0C2. F0C2 hex equals what in octal? Oh, God. How do you do that? Well, how would you do that? All right, let me give you a hint. Well, you can, but I'm going to try and do it this way. I'm going to try and use this trick a little bit. Could I convert this to binary?
No.
No? Didn't we just do it?
Yeah.
Up here? Right? We know how to convert hex to binary. Is there an easy way to convert binary to binary to octal? Right? Look at here. What if I gave you the largest 3-bit number? 7. Why is that significant? Yes, and what does it have to do with octal? That's the largest digit in octal. So again, all 8 digits in octal are represented by, at most, 3 bits. The largest 3-bit number is 7. The largest digit in octal is 7. If you count from 0 to 7 in binary, you get every single combination of 3 bits. So just like we converted 4 bits to hex, 4 bits at a time, we can convert 3 bits at a time to octal. Oh, okay. Let me not mess this up. Let's do that. So First step, convert this to, all right, let's do it in steps. First step, convert that to binary. Second step, convert whatever the heck you got in binary, convert that to octal. Okay? So let's do that. So, how do you convert this to binary? What is F? What is F in 4 bits? How do you write 15 in 4 bits? Remember, you can convert every digit in hex to 4 bits in binary and vice versa. Every digit in binary, every 3-digit number in binary to 1 digit in octal and vice versa, right? So F means what? And how do you write 15 in binary? 1, 1, 1, 1, right? Haven't we just seen this today? Okay. All right. How do you write 0 in 4 bits? 0, 0, 0, 0. All right. What does C mean? 12. A is 10, B is 11, and C is 12. All right. How do you write 12 in binary? Do you need an 8? Do you need a 4? Do you need a 2? Do you need a 1? Okay. How do you write 2 in 4 bits? Do you need an 8? Do you need a 4? Do you need a 2? You need a 1? No. All right, so that's your binary number. All right, now I'm going to take that number and use it here. All right, but the point here is that I'm not going to group in 4s. I'm not going to make this groups of 4. I'm going to make this groups of what? 3. All right, so get rid of that space, get rid of that space, get rid of that space. And now space it out in 3s. Whoa, I should put a comment thingy here. Because I'm not evaluating this, right? Okay. All right, so let's do it. All right, so how do you write 1 in octal? 1. All right, now what does this number represent? These 3 bits, how much is that? 7. Is there a digit for that in octal? Guess what it is? It's 7. Wow, this is not tough. All right, how would you represent 0 in octal? 0. How do you represent, well, what is that? 3 in octal. Well, it's 3. Okay. How do you represent 0 in octal? 0. How do you represent 2 in octal? 2. Wow, that was really hard. All righty. Any questions how we did that? Now, you don't write the answer spaced out like that, but that's how you do it, right? The answer is 170302 octal. You don't have to write those spaces. Same thing, you don't need spaces here or spaces there. It's just helpful to break it up a little bit, right? All righty. Can we check this in Sage? What if I show, quote, F0C2, wait, I'm sorry, I show the int of F0C2, which is a base 16 number. I want to show that as a base 10 number. Okay. Now, how am I going to check that everything else is correct? That's what was given. This was given. How do I check my work? Do the same thing to this, and do the same thing to this, and see that you get the same exact base 10 numbers. All right, there's a check for you. So show the integer of, quote, let's do this, comma 2. I think it doesn't like the spaces. Yeah, it doesn't like the spaces. Get rid of the spaces. What I do, I forgot parentheses. I do that all the time. Did you get the same amount in base 10? If we did this correct, all of these weirdo numbers should convert to the same value in decimal, right? This is good so far. It is, right? All right, what else am I going to check? Show what? What's my last check? The 170302 in quotes, comma 8, right? So the int, it spits out an int at base 10. we plug in a string 170302 and tell it that it's a base 8 number, so it converts it to base 10 for us. And I keep on forgetting that extra parentheses. And did you get the same thing all 3 times? So you know what you're doing is the point. Yes? Any questions how it works? All righty. This is converting everything base 10. Right? So I converted the question to base 10, the number we got in binary to base 10, which was sort of like an intermediate step. And the final answer they wanted from in base 8, we converted that to base 10, and they're all the same. Right? Remember, this is a numeral or a symbol. This is a numeral or a symbol. This is a numeral or a symbol for the same number, the same amount. All right, so they all have to convert to the same thing. Yeah. All right, who's stuck? Coming around. Here we go. They all mean the same amount, yes. Those are 3 different numerals for the same number. All right. New function, inner. Oh yeah, because that's we didn't want Sage to look at those. Just the last 3 lines. Yeah, Sage only knows how to do the last 3 lines, right? Everything else is done. Who's stuck over here? Stuck over here? Everyone's unstuck already? That was too easy. Alrighty. So you're getting good at this stuff, huh? You know how to convert to base 10. You know how to convert from base 10. You know how to convert from hex to octal to binary and backwards, right? Amazing. You even know how to add and subtract in other bases. By the way, did I ever tell you about my 3rd grade math teacher? Mrs. Sharowski. Did I? I did? What did she make us do with the first day of every month?
Oh, she converted to
Right. So you never did this. You lead a sheltered life. You didn't have a math teacher in the 3rd grade that made you do base 3?
Was it new math when you learned it?
I guess it was new math, yeah. So she would take out the calendar, right? She'd print it out, give it to everybody. Said, hello, children. See all these numbers? They're all in base 10. Convert them, to base 3. So you have to rewrite the whole calendar in base 3. The first day of the following month, okay, children, here's the calendar. Convert everything to base 5.
Wouldn't it be the same exact day?
No.
Same number.
Same number, right, exactly. We always start out with base 10 because the calendar is in base 10, I hope, right? But she'd make us change all the numbers to something else. Base 2 in September, base 10, 11 in October, base 3 in November, whatever the heck she wanted, yeah. Base 16 in December, whatever. Yeah, that's when I went uphill both ways in the snow, barefoot, with my slide rule on my back, to the Little Red Schoolhouse on the hill in Laurel, New York, on the North Fork of Long Island. Yes, it exists still today. You drive by there, the Red Schoolhouse is still there.
So you went uphill both ways?
Uphill both ways, barefoot in the snow, with my slide rule on my back. Don't worry. All righty. All right, anyhow. Number 5, you ready? What are the results written in base 2 of the following operations? 10111100 base 2 times 4 base 10. In other words, how do you multiply in other bases? Let's talk about this. All right, so number 5 says I need 1011100. Okay, 1011100 base, well, I'll just say binary. Times, let's use parentheses. How about this? Times, what is it, 4? 4 in base 10, decimal. How the heck are you going to do that? And get the answer in base 10? Convert everything to base 10 and see how it works, right? Something I said. We'll miss you. Okay. Well, yeah, that's an idea. Why don't you convert everything to base 10, do it in base 10, and convert it back to base 2? That's maybe cheating, because I think maybe it's easier than that. But let's do it. Are you ready? All right, let's do it. This is a comment. What is 1011100 binary converted to base 10? Well, let's see. No 1s, no 2s, 4, 8, 16. So we're up to 28. 16 and 4 and 8, right? 28. All right. No 32s, but so what's 64 and 28? 64 and 28. How much?
Wait, no.
82? Okay. So 82 base 10 times 4. Is it 92? We had 64 and 28. Yeah, 92. Whoa, that was weird. All right, 92. All right, so go ahead. Do that in your head. Multiply. What's 4 times 92? Normal base 10 numbers. 4 times 2 is 8. 4 times 9 is 360. 368? Is it 368? Okay, 368. Okay, now the question is, can you convert that back to base 2 is what they want in the final answer. How to convert 368 to base 2? Well, let's see. All right, is 1's place enough? No. Is the 2's place enough? Oh, God. Is the 4's place? 16's place? No, sorry, 8's place. 16's place? Oh, jeez. 32nd's place? 64's? 128's? 256's? Well, 512 would be too much, right? Okay, all right. So we're up to 1's, 2's, 4's, 8's, 16's, 32's, 64's, 128's, 256 place. So how many 256's do you need? What is... What? 1, really? Okay, what is 368 div 256? It's 1, but what's the remainder? What's the mod? 256. 112. Okay, so do you need a 128?
Yes.
128 fits in 112? No. Okay. Do you need a 64?
Yes.
How many 64s go into 112? 1. Remainder? What the hell was it? 112 minus 112 minus 64? What's 112 minus 64? 48. All right, so do you need a 32?
Yes.
All right, so how many 32s fit in, what did you say? 48. 32 into 48? 1. Remainder? 16. So do you need a 16? Yes. Do you need 8? No. Do you need a 4? Do you need a 2? Do you need a 1? Okay. What just happened? I know. But compare your answer to where you started. You just added 2 zeros. Don't you know that? Wait. In base 10, when you multiply by 10, you add a 0. When you multiply by 100, you add 2 zeros. Well, here we multiply by 4.
Add 2 zeros.
Add 2 zeros. Right? It's the exact same thing. Do you see what I was saying? When you all right, let me just take a look at this number. What is 368 times 10? All you do is add a 0 at the end. So 3680, right? Times 100. Add 2 zeros. Times 1,000. So 368,000, right? But that's 10 to the 2. Right? If you multiply by 10 to the 1, add 1 0. You multiply by 10 to the 2, you add 2 zeros. You multiply by 10 to the 3, you add 3 zeros. Well, what's 4? 2 to the 2, so add 2 zeros. What if I was multiplying by 2 instead? So get rid of one of these zeros, right? What if it was an 8 instead? All right, so now the next question's easy. What if you divide by 4? Get rid of... How do you divide by 100? You get rid of 2 zeros, right? How do you divide in base 10, right? How do you divide by 4 in base 2? Get rid of 2 zeros, so you're done. All right, so this is 5A. 5B is divide. I'll put it right here. Is what happens if you divide, and all you do is lose 2 zeros that you had. We'll lose these 2 zeros. All right, so it's 1, 0, 1, 1, 1. That's it, done. That's it. Just take off 2 zeros. We're dividing by 4, so chop off 2 zeros. Multiply by 4, add 2 zeros. Divide by 4, chop off 2 zeros. That's it. Is that true? Well, can you divide 368 by 4 in your head? What's 368 divided by 4? No? All right, let's ask Sage. What is 368 divided by 4 in base 10? Now, is this 92?
Yes. No,
No, it's not at all.
It's not. Wait, did we mess up?
It's 368.
No, this is 368. We chopped off 2 zeros. What is this?
368.
No, we chopped off 2 zeros. Can't be the same. Is it 92?
No.
A 1, a 2, a 4, an 8, a 16. Wait, something went wrong. Did I copy something wrong? Oh, that's the answer after you multiply by 4. Whoa. Yeah, whoa, that is 368. Yeah, sorry. Wait, no, what is this number before you divide by 4? Sorry. No. If we divide by 4, we get 92. So this better be 4 times 92, which is what? No. I'm confused. What have I done? All right, wait, let's do it. No 1s, no 2s. It is 92, right. Oh, okay. So the question is, what is 92 divided by 4? Sorry. It's 23. Is that what this is?
Yes.
Oh, okay, sorry. I know how to do the problem, I just don't know how to check. Sorry. The easy part's the hard part for me. Okay.
Can you scroll up?
Scrolling up. This is scrolling up. Is that what you want?
Yes, that's what I want.
Are you sure? Okay. Okay, just checking, because people usually don't want that when they say scroll up. Move the paper up. Right, the scroll is the paper.
If I say move the paper, I can say scroll up.
Yeah, be one with your inner pharaoh when they used papyrus scrolls for real. All right, so you ready for 6? We're ready to write some code. We're going to have to write a function here. Remember writing functions? Okay, Christian, hang on to your hat. This is a baptism of fire for Christian. He hasn't seen this yet. How do you write a Python function to do the following? Number 6, write and test a function that counts and returns a number of bits, binary digits, set to 1 in a positive integer. So define count bits n, returns a count of bits set to 1 in a positive integer. For example, if you plug in 12, you get 2. Huh? What? Why? Well, look at the explanation. Well, 12 is 1100. They're plugging in a base 10 number, 12, and they're counting the number of ones in the binary representation of 12. Right? So what if I plugged in, I don't know, something else. What if I plugged in 7? What's count bit 7? It's a 111, so the answer would be 3. Do you see what we're doing? So how do we write a program that does this for us? All right, here we go. Number 6. Define. Count, was it count bits? Okay. Count bits of n. Colon, enter. Remember it automatically indents for you? Don't forget the colon. All right, so what's a function? It's like a little piece of code. It's like a mini program that you plug in something, and it calculates stuff, and it spits it out for you, okay? All right, so look, there's hints. Oh, there's hints. So goody. Check the digits from right to left. In other words, from the ones place first, then the tens place, then the hundreds place. Okay. N div 2 returns the rightmost or least significant digit in the binary representation of n. What? Why? What if we did 12 div 2? What is 12 div 2? 6. Is that I'm sorry, I said it wrong. What's 12 mod 2? That's a mod. 0. Isn't the 0 the rightmost digit in 12 when you write it in binary? Look at it, they show it to you there. It says 12 is 1100. Okay. So n mod 2 returns the rightmost or least significant digit, the ones place, in the binary representation of n. A mod b is read a modulo b and means the remainder when you divide. Okay. Also, n div 2 divides n by 2 and truncates the result to an integer, in effect shifting the binary digits to the right 1 and getting rid of the least significant digit. So, oh, interesting. Okay, so now let me ask you again, what's n div 2? That is 6, right? How do you write 6 in binary? 1, 1, 0. Isn't that chopping off the last digit of 12, which is 1100? So can we use that in a loop to figure this out? Yeah, perhaps. But you know what? I think we're out of time, aren't we? All right, so let's save it here. All right, we'll do 6 and 7 tomorrow, writing some functions. All right, so I'm going to republish this so I can throw it on my blog. And I'm going to save and quit, so it's there. And it's published, right? Yep, there it is. See, I'm not the only one publishing here. That's me, that's not me, that's me, that's me, that's not, that's me. That's not me, that's not me, that's not me, that's not me. That's me, that's me, that's not me, that's me, that's not me. That's me, that's not me, not me, not me, me, not me, not me. Wow, look at that. There's a lot of stuff on here. All right, have a nice day, guys. See you tomorrow. Finishing up 5-3 tomorrow. Oh, and I gotta say bye-bye to YouTube. Bye-bye, YouTube.